Basic sorting for software developers. When we have a few objects, be it of any kind, and we want to sort them, this means that we want to rearrange them somehow so that they follow some ordering, an ordering that we define. We can take, for example, one of the fields. If we have ships that we want to sort, so we have on our field a list of ships, they're eating the grass and we want to sort them. Each ship has a name, and we want to order the ships by their name, lexicographically. We could also say that we want to order our nice ships by their age. So we would, in this case, we order them by their age. So we choose a specific field. Usually in sorting we call this the key that we sort by, and we sort by this key the original objects. We choose some quality that we have of this object, and then we rearrange all these objects. In the lexicographical sorting, so if we have two ships, one named Avida and the other one is named Guliantra, then lexicographically Avida should be before Guliantra. Although Avida could be of a larger age, it could be older, but we are sorting by their names. So, respectively, we could sort the sheep that we have by their age or by their name or by any other quality that we choose. In computer algorithms, sorting is like the basic algorithm. It's like the mother of algorithms. These are the algorithms that you study first. And once you have these algorithms, you would find that they are also the basis of other algorithms and other problems, because in other problems you would find that you need to first do some kind of sorting in order to resolve the problem. So sorting could be found out to be the first step of many other problem solutions. While there are many types of sorting algorithms, we have a few shared metrics to evaluate them all. Some of these metrics we use to evaluate other algorithms, not necessarily sorting. So if you refer me to a specific algorithm, you have your own algorithm of sorting, then I could ask you these questions and we could check these metrics of your algorithm, and so we could compare your algorithm to other algorithms. This is like the sorting of the sorting algorithms. So what are the questions that I could ask you of your sorting algorithms and of any sorting algorithm? I could ask you, is this sorting algorithm stable? Is it sorting in place? What is the average and worst and best case running time of this sorting algorithm? Which type of data is this sorting algorithm best suited for? How much memory does this sorting algorithm requires? And does it need actually extra memory relatively to the input of your algorithm? So let's go through these terms: stable, in place, running time, and memory terms. Stable sort. Once we sort a few ships from our sorting example, Let's say we sort the ships by their yearly age. So one ship is 4-year-old, one ship is 5, and hopefully some others are older. So it might be the case that a few ships have the same yearly age. And now we check what is this stable sorting. When we say that a sort is stable, what do you mean? Or when I ask you, is your sorting algorithm stable? What do I mean and how do you answer this question? So the question of whether a sorting algorithm is stable is basically this question. If the ships are originally all lined up, but not sorted of course, they are not sorted by their yearly age yet, and then you take your algorithm and sort them by their yearly age. Then if two ships have the same age, would they have a different relative ordering after the sorting is done? Note that we didn't say an absolute order, of course, because it might be well the case that the two oldest ships with the same age are lined up at first on the beginning of the row and we move them to the end of the row after we sort it. The question is just if when you sort and lined up these oldest ships at the end of the line because they are the oldest, then do you preserve their original ordering? If your algorithm always preserves this relative ordering, then we say that your sorting algorithm is relative ordering preserving for equal items, or in other words, your algorithm is stable. This is a stable sort. Stable sorts algorithms are including merge sort, it's stable, insertion sort, it's stable, radix sort, it's stable, team sort, it's stable, and bubble sort, it is stable. Unstable sorts include heap sort, for example, and also quick sort, which are both not stable. The next question I could ask you about your sorting algorithm is whether it is in place. What is an in-place sorting algorithm? When we ask if sorting algorithm is in place or not, we actually ask about how much extra memory it's using. As long as it's using a constant amount of memory relative to the list that you sort, then we say that it's in place. You can use additional memory for your sorting, of course. No one is blocking you from adding variables and using extra memory. That is all fine. But the question is whether this extra memory is of constant space, meaning it's not growing. This extra memory that you are using is not growing relatively to the number of items that we are sorting. It does not matter how much extra memory you need in your sorting algorithm. It does not matter if you need an O of n log n extra memory or O of n or O of n squared, lo behold. As long as the additional memory that you need is of constant amount, O of 1, we say extra memory, meaning there is no relation to the number of original items that you sort. As long as it's constant, then this means that you can sort basically as many items as you wish. And your sorting algorithm must only use this extra constant amount of memory, and then we can call it an in-place sorting algorithm. It's sorting it in place. It does not need some relation of the original list of extra memory. It's a constant amount of memory that you add in order to sort these items. Then we can call it an in-place sorting algorithm. Now let's take as an example one of the most basic sorting algorithms and check its qualities. We are going to ask if it's stable or not, if it's in place or not, and examine how does it work. So bubble sort is a stable sort, which means if you have two equal items, then the ordering between them would be stored in the output sorted array or list. It's also in place, which means it's using a constant additional amount of memory. Okay? And its best time complexity is O of n. Its average time complexity is O of n squared. And its worst time complexity is also O of n squared. And space complexity, the additional space that it's requiring, is a constant space O of 1. In bubble sort, we compare each successive pair of elements in the given input list. And if we see that this pair that we are looking at currently is not ordered, then we invert the ordering of them. We invert them, swap them. After we finish one iteration of scanning the whole list, comparing each two items and replacing each such pair, if they are inverted originally in the ordering, then we see that if we started the comparison from the beginning of the list and we swap if the left item is larger than the right item, then we would end up with the largest element at the end of the list after one iteration. Bubble sort is also known as sinking sort because it's repeatedly comparing each two items and swaps them if they are at the wrong order. Then it does this process again until everything is sorted. So the items are like syncing to one end of the list, and this depends if you start from the beginning to the end or from the end of the list to the beginning. And after one iteration of comparing all the pairs, you're sure to have one item sorted. If you scan the list once and you compare each two items and invert, if it's not ordered, then you're sure to have one item sorted, either the smallest or the largest one, depending where you started. You would have the largest item in its place if you started from the beginning of the list. And after two such iterations of scanning the whole list and comparing each pair and checking if they are inverted and replacing and swapping if they are inverted, then you are sure to have the two largest items at the end of the list. We said that the best running time of bubble sort is O of n, and that is because if we scan the list once and we see that we do not need to swap any two items because everything is in order, any pair that we checked is in order, then we can just shortcut and end it and say, hey, we scanned the whole list, we compared each pair, and we saw that we didn't need to replace any and didn't need to swap any two items, so everything is sorted. So the best case running time of bubble sort is O of n. To sum up, when we are sorting a bunch of items, then we usually look at the key of some property of the items and we sort by it. Of course, if we just have a list of characters and we want to sort the list of characters, then we could check the ASCII code of the characters and compare it. But this is also a quality of the character. We said that we choose one property of the items and we sort by it. Then we said that we have multiple qualities for sorting. For example, we check what is the running time, whether it's a stable sort or not, whether it's an in-place sort or not. In-place means we just need a constant amount of memory, additional constant amount of memory in order to do the sorting. This is in place, and the stable sort means simply that if we had a pair of items then which are equal, then the relative ordering is not changed. And we said that we have an example of stable sorts, which include merge sort, insertion sort, radix sort, team sort, and bubble sort, and unstable sorts, for example, are heap sort and quick sort. Then we went through bubble sort and we said that its best running time is O of n. It's linear. Because if we scan the list and everything is okay, then we scan the list at least once and it's okay. And that's it. We at most once also. But its worst time complexity is O of n squared because we needed to scan the list multiple times. At most, O of n squared of the times that we need to scan the list in order to sort everything, because we compare each pair and we bubble, and in each iteration we fix one item. So we need n minus 1 iterations of these pairs. If we have n items, then we need n minus 1 pairs comparisons. Each time we need to compare all the pairs. And we saw that bubble sort is stable because we didn't need actually extra memory relative to the input number of items. We only needed a constant amount of memory, and its worst time complexity is equal to the average time complexity, which is O of n squared, and its best time complexity is just scanning the list once. So that was it today for basic sorting. I hope you enjoyed it. I did, and I will see you next time.